of, suppose that C is a constant and the limits are below. What they're saying is if you have a limit of more than one function doing an operation together, you can write them out as separate limits. So for example, the limit as x approaches a of f of x plus g of x, I could write that out as two separate limits. The limit of x approaches x of a of f of x plus g of x. Same thing with subtraction. If C is a constant, so if C is like the number 2, let's say, or 8, or -4, I just, it follows behind a function, I can take that C out and then do the limit of that function. Same thing with multiplication, you can write it out as 2. Same thing with division, you can write it out as 2. Just the key thing is that your denominator can't equal 0. So we're going to use the limit laws and the graphs of f and g in the graph below to evaluate the following limits if they exist. So we can do these ones separately if we want to use those limit laws. We can go the limit as x approaches -2 of f of x. And then we can add the next one, but if you see here, this is a constant function. We can either leave it in there and multiply it by the g of x, or we can completely pull it out in front and find the limit as x approaches -2 of g of x. Now remember, the limit is not specifically what the value is at that x, it's what it's approaching from the left and the right, and it has to be that same value, right? So a point of discontinuity can have a limit and not exist, because the limit is what it's approaching. So if I look here, I want the limit as x approaches -2. Well, I have to check from the left and the right and see if it's the same thing. Okay? So this is of the f of x graph. So I go -2. From the right, it's approaching what? Or sorry, from the right. From the left, it's approaching what?
1.
1. From the right, it's approaching what?
1.
Does it approach the same value?
No.
Yes. So the answer to this is 1. Right? Just from the left, from the right, if it's approaching the same thing, it's that value. Then we get the plus sign, 5, and now I have to find this. So now I need a limit as x approaches -2 on the g of x graph. So I go to -2, and from the left it's approaching what? -1, and from the right it's approaching -1. So this would be -1. See what I'm saying? And then you just math. 1 plus -5, and what's my answer? -4. So technically on the graph of f plus 5g of x, so if I took these two graphs and I made the graph of f plus 5g of x out, at -2 it would be approaching -4 on the y. But it would be way harder if I actually had to do that and make that new graph. It would be a lot more work, which I would not like to do. Okay, the next one is multiplication. So I can actually split that up into two limits just being multiplied together. So instead of the limit as x approaches 1 of f of x g of x, I can go the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. And then this one would be division. So it would be the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. So try those two out, see if you can get the answer. All right, so we have the limit as x approaches 1. The limit as x approaches 1 of f of x is 2, if it joins me. It's 2. So we get 2 times the limit as x approaches 1 of g. So from the left, it's approaching -2. From the right, it's approaching -1, which is a problem. So left limit's perfectly fine. Right limit's perfectly fine. Limit there doesn't exist because it has to be from the same place. So it should be 2 times does not exist. That is not actual math. You can't do 2 times does not exist. It's just does not exist. So this limit just does not exist. The moment one of them doesn't happen, all of it's gone. Okay? Then we have the limit as x approaches 2. So as x approaches 2, from the left of f of x, it looks like 4.57. Okay, cool. I'm going to go with 1.4. And then g at 2 approaches what? 0. So it does not exist as well. Because as you guys know, you would end up getting some sort of asymptote, something point discontinuity, something like that. But you can't divide by 0. We agree? Okay. Next page. It's the new booklet in front of you. So we're going to evaluate the following limits. So today we're doing limits. We're doing one-sided limits. And then tomorrow we're doing squeeze theorem, and we're doing continuous functions. How to tell something is continuous at a specific x value. Okay, continuity. The limits unit isn't really long. The unit exam for limits will be worth half of a unit exam because it's a much shorter unit than the rest of the 3 units, just so you know. Okay, so we have the limit as x approaches 5. So if you can plug in and there is no problems, then you can. Like if you can plug it in right away and we don't get a denominator equal to 0, then we can just substitute and get the limit. Because what's happening is, this is a quadratic, correct? It's a parabola, yes? Parabolas are continuous. So from the left of any x value and the right of any x value, you're going to land at the same value as the actual value itself. Because your only errors or problems happen when you point to discontinuity or gaps in your graphs or asymptotes, etc. So if you can just do direct substitution, then that would be your first step. So if I have the limit as x approaches 5 and I want to plug it in, remember I have to keep the limit word until I substitute in. The moment I substitute in, the limit word goes away. Because that's telling us what number we're going to substitute into here. So we're going to get 2 times 5 squared minus 3 times 5 plus 4. And so we get 25 times 2, which is 50, minus 15, plus 4, which is, what do we get? 39. So from the left of 5 and the right of 5, it's approaching 39, and actually at 5 it's approaching 39. It is 39, because it's a continuous function. The next one, some people think we have to do something first. They want to go factor it and all that jazz. You don't have to unless when you plug in it makes the denominator be 0, correct? If I plug negative 2 in there, my denominator isn't 0, is it? So I can plug it in. Direct substitute. So the limit's going to drop off because in the next step I'm going to plug in negative 2. I get negative 2 cubed plus 2 times negative 2 squared minus 1 all over 5 minus 3 times negative 2. And so I get negative 8 plus 8 minus 1 all over 5 plus 6, which is 11. So I get negative 1 over 11. Look, Kyle. Pretty yellow. I believe in you. Did you get it? You did. That's okay. Direct substitution property. If f is a polynomial or a rational function and a is in the domain of f, then you can just directly substitute it in. However, what's the problem with number 3? Yeah. Yeah, it's going to make a 0 in the bottom. And are we allowed to have that? No. So we can't direct substitute right off the bat. We have to do something to try and get the problem away. And the problem is the x minus 1. If I can get that x minus 1 to cancel off, I can plug in and I'm fine, right? So the first thing I'm going to do is rewrite the limit. Is there some sort of algebra I could do to this? Possibly the numerator? Yeah. Difference of squares. So I'm going to send you off into the world with the prof saying, wow, these kids really know where to put equal signs. That's what my goal is. and also to do calculus. But besides that, top notch, they know how to use an equal sign. Okay? So this limit here equals the next step, correct? So we're going to have equal signs, equal signs, equal signs. So I keep the limit, the word limit, because the only time I get rid of that word limit is if I substitute the 1 in, and I'm not, correct? If I substitute the 1 in right now, I'm going to have 0 in the denominator, and that's a problem. So I factor the numerator, and I get a difference of squares, which is x plus 1, x minus 1. In the denominator, I have a binomial of x minus 1. And that is my issue, that x minus 1 needs to go away, because currently I can't substitute in because it's there. Well, when I factored the top, I see now the numerator, I see that we actually have some things that match. I used the same side of the pen, but it changed colors because it felt like it. Okay, so now I have an x plus 1 in the numerator. If my denominator completely cancels off, do I have to write a 1 in the denominator? No, every number is over 1 if it doesn't have a denominator. Its denominator is 1, right? If the numerator completely cancels off, do I have to have a 1? Yes, because if it cancels off, and I need to place it, it needs to be like, if it was something over 4, if it canceled off, it needs to be 1 over 4. If not, you'd say it's 4, which is not true. Okay, our issue is gone now, so we can substitute in. So the moment we go to substitute in, the limit goes away, right? So I'm going to plug the 1 in. So I'm going to get 1 plus 1. Do you see how I don't have the word limit anymore? Because I substituted in for that x. And your answer is 2. Now, guys, because those factors canceled off, what is actually on this graph at 1? A POD. Now, in calculus, they call that a removable discontinuity. You're welcome. That is what they will call it from now on till the end of time. They call it a removable discontinuity because they also have some things that are called jump discontinuities, which means like you could have the removable discontinuity. A jump discontinuity is where you start here and then you jump and you come back up here and it's another piece. They call it removable, not a point discontinuity. I don't know why 30-1 doesn't just call it removable discontinuity, but we don't. So on the left and the right, this is approaching 2, and then it's open at 2. Here, this needs a squiggly bracket, because that's what piecewise functions have. Put yourself a little squiggly bracket in there. Or a weird-looking S, if you can't do a squiggly bracket. So it's a piecewise function. Let's understand what this means. So on this graph, there is a coordinate at pi and 1, correct? I said it wrong. 1 and pi, correct? So this would mean for x equals 1 and only 1, the y value would be pi. So that's a coordinate, 1 and pi. The rest of the entire graph is represented by the line x plus 1. But at x equals 1, I have an open dot on that graph because it can't equal 1. You see that? It says x can't equal 1. So we have a line drawn at x plus 1, but when x equals 1, you have an open dot and then 1 pi. So what does that look like? I have a y-intercept of 1 and I have a slope of 1 over 1. So it's like, come on, oh my gosh. So like this, then up 1 over 1, except it's an open dot. Really? Love newborns. They're awesome. So that's back to oh wait, there's an open dot there, and then we keep going like this. And then at 1 and pi, I have a closed dot. 1 and 3.14. That's technically kind of what the graph looks like. We agree? There's a whole entire line, x plus 1, open dot at 1. And then there's a coordinate at 1 and pi. So they want to know if we can find the limit as x approaches 1 of g of x. So we have to do from the left and the right. I can see right now that there is a limit. It exists because I drew it. But what if I didn't draw it? How can I show it algebraically? So I do the limit as x approaches 1 from the left. Now I need to pick which equation represents less than or equal to 1, or just less than 1, sorry. What equation represents less than 1? The top or the bottom? The top. This one represents anything but 1, right? So I would plug it into that one. So I have x plus 1, and then I get 1 plus 1, which is 2. Then I have the limit as x approaches 1 from the right. So it's greater than 1. Well, it's still the same one because this one is only when it's equal to 1. So I get 1 plus 1 equals 2. So from the left and the right, it approaches the same thing. We agree? Yeah. Yeah. So then we have to say, therefore, remember the 3-dot triangle means therefore in mathematics? Therefore, the limit as x approaches 1 of g of x equals what? 2. Example 5. Can I direct substitute? If I plug a 0 in, am I okay? No. Some people say multiply by the conjugate. Remember, the conjugate is when you have radicals. Do we have a radical currently? What's the only thing we could possibly do? Yeah. Expand out the 3 plus h. But remember, when you expand it out, you have 2 of them. You don't have 9 plus h squared, correct? You have to FOIL it. You're going to get a middle term as well. So I'm going to rewrite the limit. Limit is h goes to 0 of 3 plus h squared minus 9 over h. So it's the limit as h goes to 0 of 9 plus what? Nope. 9 plus what? I'm not going to skip this step because I feel like I lost a few of you. So what is it? 9 plus what? 3h and? Which is? 6h plus h squared minus 9 all over h. What could I do next? Yeah, take a GCF of h out of the numerator. Because the h in the denominator is my issue, right? If I can get that h to cancel off, I can do direct substitution. So I'm going to get h bracket 6 plus h all over h. The h's cancel. And now my issue is gone. Yes? So now I can substitute in. And the moment I substitute in, the limit word goes away. So I'm going to get 6 plus 0, which is 6. So the answer to that is actually 6. Okay? And we're going to flip over. Yes. Okay, I want you guys to try this one out. When stuck with a radical, what are you probably going to have to do? The conjugate. Multiply by the conjugate. Try it out. Okay, so remember, why do we multiply by the conjugate? What is the key reason to multiply by the conjugate? Yeah. Get rid of the radicals. So you square the first 2 terms. If they have radicals in them, they'll become that. Square the back 2 terms, they have radicals, they'll become that. And the middle terms should be opposite and cancel. That's the point of multiplying by the conjugate. It's so that you actually rationalize, which means get rid of the radical. That's why it's called rationalizing. So we get t squared plus 9 times t squared plus 9, sorry, root of them, which is just t squared plus 9. And then if I want to show all the work, outside I'm going to get plus 3 square root t squared plus 9. In the middle, I'm going to get minus 3 square root t squared plus 9. And then negative 3 times 3 is negative 9. All over. Now, the two that are not conjugates, I've told you this numerous times. Do not put them together. Leave them separate. Why do I leave them separate? This t squared here is my problem. If I plug a 0 in, it's going to cause me issues, yes? So I'm trying to get the t squared to cancel off. If I distribute the t squared into this ugly radical thing, am I ever getting the t squared to cancel off? No. So the people who distribute the denominator or the one that isn't the conjugate together will be stuck on these questions all the time, and the people who remember to leave them separate will get these right every single time. Okay? So we're going to leave the t squared separate, and then we just rewrite this separately beside it. Now, if you did the conjugate correctly, your middle terms with radicals should cancel off. That is the point. And then in the top, I'm going to keep my limit as t approaches 0 because I can't plug in yet until I get that t squared to cancel off. The 9 and the negative 9 cancel off, and I'm left with t squared over t squared, which also cancels. So what am I left with in the numerator? 1. 1 over square root t squared plus 9 plus 3. Why is it changing colors? My next step, now can I substitute in? Did I get rid of the problem? Yes, so I can substitute in. I get 1 over the square root of 0 squared plus 9 plus 3, which is 1 over the square root of 9 plus 3. Square root of 9 is 3, so 3 plus 3, which is 1/6. We're going to finish the middle stuff after. That doesn't take your 9 at all. But your homework is below.
So we're going to do our homework now and finish the middle stuff after.
Yeah, where the heck? I didn't print the next page. You have it in front of you. You're working on everything but the last number. Everything but 36.